Hello and welcome. My name is Ambrish Tripathi and I am an apps engineer at Texas Instrument. The subject of this talk is how to power automotive front-end systems. This talk is split into three parts. This is first part where I will be covering automotive ADAS processor power supply design. Here is the agenda of the presentation. We will go into the details of automotive front-end power block and also review two ADAS power solution. The first one is an example of a 30-watt automotive ADAS reference design for a typical surround view system, and this will include all the protection. And the second reference design will be a complete automotive camera module design where we will go into the details of EMI requirements, POC filter requirement, the power over coax filter requirement, as well as input voltage transient requirement. This is a generic block diagram of always on automotive system in all battery condition. So what are the key features of the block diagram? Now the first feature is the system must maintain a constant output voltage over the full DC range of battery condition specified in the OEM standard. Now here the VIN can go down to 3.2 volt simulating a severe cold cranking condition, or the input voltage can go up to 18 volt simulating the upper range of normal battery operation. Also, the system must clamp, filter high voltage electrical fast transient and maintain operation through them. These pulses include load dump, which is specified by OEMs and is about like 27 to 30 volts. And it may include other transient outlined in ISO 7637 Part 2 standard. The system must properly also respond to a reverse polarity event and should shut down. The design should also comply with CISPR 25 automotive EMI standard, both radiative as well as conducted EMI. So here are the details of automotive front-end design. We have divided the automotive front-end design into four parts. The first is reverse battery protection. Also we will need to have a transient protection, which we will take into the details. So we need to have the reverse battery protection. We need to have a pre-boost system here. Also we will go into the details of wide VIN buck converter and this supervisor if needed. So why do we need reverse protection for any automotive system? It is needed to protect the system against the battery being attached with the reverse polarity. That means you put the positive and negative in the opposite order. Now traditionally, diodes have been used for lower current application, but they dissipate a lot of power because of the diode drop. In higher current application, traditionally multiple diodes are used in parallel to spread the heat. In some cases, high side PFET or low side NFET with external bias component is most efficient compared to the diodes, and they support higher load current, but they are larger and more expensive. So what is the solution? The solution is to use a charge pump controller with the high side NFET, N-channel FET, which will provide more integrated solution and will also reduce quiescent current. Now let's go on to the details of pre-boost requirement. First of all, we need to support the lower VIN in the case of cold crank start-stop and as well as warm crank condition. The switcher needs to switch outside the AM band, either below or above AM band. And also a synchronous solution is more common, particularly for low wattage and mid wattage pre-boost application because of its low cost and easy designability. So let's move on to the requirements of wide VIN buck converter. Now the wide VIN buck converter needs to support voltage up to 36 volt. Also, traditionally the wide VIN buck converter, the automotive wide VIN buck converter used to switch below AM band. And what is the disadvantage of the switches switching below AM band? Basically, the harmonics will still end up in AM band, and it will need a lot of filtering to filter out the harmonics. Now, when you switch above AM band, there will be absolutely no harmonics, and also the size of the input filter will be much smaller, as well as the output inductor as well as the capacitance size will be much smaller and will result into the size minimization of the system. Further, for synchronous converter is preferred for output current less than or equal to 3 amp. Now, for the supervisors, they are basically used to monitor system voltages and also to trigger a control power down sequence when detecting a falling or out of range supply voltages. For point of load DC to DC converter, remember what is the input voltage for point of load DC-DC converter? These are low input voltage, 3.3 volt or 5 volt. And generally, the switches above AM band at higher frequency. The multi-phase solution is preferred, interleaving is preferred, and size is usually a concern in these systems. Therefore, typically they are very small integrated solution, of course with high switching frequency and with very small inductor and capacitance sizes. To support our automotive customer designing ADAS power supply, we have built a large library of power solution optimized for cost, EMI, and input voltage transients. They show proof of concept and are a great vehicle for the customer to look at during their evaluation phase. We will go into the details of PMP 10653 as well as PMP 10652. Now PMP 10652 is a ADAS 30 watt system level power supply design with all automotive protection as well as it meets the EMI standard. PMP 10653 is a complete camera module design, and we will go into the details of EMI, POC as well as the transient requirements there. So this is a system block diagram of automotive power solution for a typical surround view ADAS system. So the power solution ranges from 15 watt to 30 watt for a typical surround view system. Now the application here uses two core. One is the master and another is the slave core, and each core in this particular application needed 4 amp at 1.2 volt output. Now let's start with the front end here. Now the front end protection is taken care by the TVS and the smart diode. So why do you need TVS at the front end? So the TVS, which act as a transient voltage suppressor, are used to meet ISO 7637 Part 2 pulse standard, and the reverse protection is ensured through smart diode here. Also, the design is tested against CISPA 25 class 4 regulation limit, and hence you can see the EMI filter here used at the input. Now there are like two LM53603 2.1 megahertz wide input voltage DC-DC converter are used to provide power to the two core. We will go into detail of this exciting 2.1 megahertz automotive switcher later in the slides. For point of load solution, we have used TPS 57114, which is a point of load 4 amp 2 megahertz solution. Here we have used charge pump TPS 60150 to supply the power for CAN communication. This architecture eliminates the need of pre-boost at the input for start-stop application and thereby reduce the cost. You can see with the front-end DC-DC converter, even with this high switching frequency, we can have a 3.3 volt output at the wide input voltage from 4.5 volts up to 36 volt input. And hence, even if you have input voltage of 6 volt at the input in the case of start-stop application, or 4.5 volts in the case of warm crank condition, this DC-DC converter will still maintain a 3.3 volt output here, and hence you don't need a pre-boost at the input, and for 5 volt CAN communication you can just use a charge pump here. PMP 10652 is a 30 watt ADAS system power driven design with EMI compliances. The design uses all the parts which are automotive qualified. Further, all the DC-DC converter used in this system switches above the AM band. Also, we have used 4-layer board for this particular design. Now let's go into the details of this exciting true 2 megahertz DC to DC converter, which provide front-end solution for the ADAS design. Now this particular DC-DC converter is of course fully integrated DC-DC converter. It's a synchronous. It offers a 2 amp or 3 amp output. And this is a true 2 megahertz DC-DC converter. So now first let's go into the detail of true 2 megahertz DC-DC converter, and we will come back to this slide again. So what is true 2 megahertz DC to DC converter? Putting 2 megahertz on the datasheet is very easy, as most DC-DC will operate at that frequency. But in reality, how the device operates at that speed is more important, as it affects the system. Here, as you can see in this graph of switching frequency versus input voltage, the red trace represent the performance of LM53603, and the blue trace here represent the performance of the competitor device. Now what do you see at the high input voltage when the minimum on time is reached? The blue trace here exhibit poor performance when the minimum on time is reached at the higher input voltage. Now the blue trace will exhibit poor noise performance and will likely need additional circuit to compensate for the behavior. Now you compare that with the LM53603 performance at the high input voltage, where there is a smooth frequency fallback when the minimum on time is reached. You can see a smooth frequency fallback, and hence offer much better solution at higher input voltage. Now let's move on to our deep dropout condition at the lower input voltage. Now here again you can see LM53603 has much better performance compared to the competitor device. And what is the reason? The reason is the much smaller minimum off time compared to the other switcher here. So overall, LM53603 perform at 2 megahertz over wide input voltage. You can see here from close to 7 volt to up to like 20 volt input at full load, you can assume this DC-DC converter to switch. You can expect this DC-DC converter to switch above AM band. Now let's return back to this slide again and look at the transient performance when there is a load transient here. Now towards your right you can see two graphs, one which is basically the performance of LM53603 and the other which is the performance of a competitor device at high VIN voltage. Now the data is taken at 28 volt input. Now what you can see is, because at high input voltage when the minimum on time is reached, the competitor device perform really poorly, and just a moment ago we were talking about it. You can see very high ripple. And even more problematic is the transient from high load to the no load, and you can see this overshoot which can kill other system connected to the output of this DC-to-DC converter. Now compare this performance with LM53603 load transient performance. You can see absolutely no noise here at the no load, as well as the transient here is minimum, and it's because we have already taken care of this automotive requirements, and hence LM53603 performs much better compared to most of these DC-DC converter available in the market. Also, this particular device supports up to 150 degrees C junction temperature, and also have an excellent light load efficiency and the IQ in the range of 20 microamp. So we tested PMP 10652 board for conducted EMI performance, and as you know, for conducted EMI for automotive system we need to do two tests. One test is from 0 to 30 megahertz and another is from 30 to 108 megahertz, and the critical is the performance in the FM band, which is from 88 megahertz to 108 megahertz, which is most stringent to comply with. Now this particular solution comply with CISPR 25 class 4, and you know, for EMI optimization for any automotive design, it is very important to choose IC with pinouts that were designed with EMI performance in mind. So in all our new DC to DC converter, automotive DC to DC converter, we have tried to innovate with both packaging and pinouts to optimize EMI performance. What you can see here is VIN is placed next to the P ground. So what is the advantage of doing this pinout here? Basically you can place the high frequency bypass capacitor, which will minimize the critical input loop and thereby will reduce the EMI. So remember, you have a discontinuous input current in the buck converter, which will result into the input voltage ripple and will generate the EMI. Also, the C-boot is placed next to the switch node, and by doing so again we minimize the loop area here so that you can put a small cap between switch node as well as between the C-boot. The feedback components now can be referenced to the quieter A ground, and remember this feedback is also away from this switch node, and so that no noise couple back to this feedback pin and thereby ensure stable operation. So by giving this pinout, you will ensure a good system level layout and thereby will minimize the EMI and hence the EMI performance here. This EMI performance is taken without any common mode choke or shielding. So we've already talked about the EMI. Now the next big requirement in any automotive system is the front-end protection through TVS. Now this particular reference design was tested against ISO 7637 specified positive and negative pulses. Now the positive and negative voltage are the results of inductive wire harness. You have long wire running in the automotive system, so you have the inductive wire harness. Or you may also have parallel inductive load connected to the automotive system. And the worst part is these pulses can go up to plus minus 75 volt. Now the question is how to protect the automotive system against these pulses. And the solution is to use the bidirectional TVS to clamp both the positive and negative voltage. But in order to choose this TVS here, what do you need to know? First, we need to know the clamp voltage, and the second, we need to know the peak power rating of the TVS. So let's go into the parameters here. So the parameter mentioned on the right bottom of the screen is of ISO 7637 pulse 2A, which simulate transient due to sudden interruption of currents in a device connected in parallel with device under test due to inductance of wiring harness. So what will happen? This will generate, of course, a positive going pulse here. You can see this positive going pulse here. Now for clamping the positive going pulses, what you need to do, you need to clamp above the double battery voltage or the jump start voltage, and also we need to clamp above the central load damp voltage, which is specified by the OEMs, which is typically about 27 volt. But this clamping voltage needs to be lower than the maximum operating voltage of the downstream devices. So in this application, 30 volt TVS is chosen. Now the 30 volt is above 27 volt load dump voltage and also below 36 volt DC to DC converter voltage. Further, we need to know now the power rating of the TVS here. You can easily simulate this transient here. Now the VG1 here can be a 50 volt source with the source impedance of 2 ohms. Now first of all we need to calculate the current which is flowing in the TVS here. So you have this 30 volt clamp. So 50 volt minus 30 volt divided by this impedance of 2 ohm, that gives you 10 amp of current. Now when you multiply that 10 amp with 30 volt clamp voltage here, you get around 300 watt of dissipation. But the second important thing is in what time we need to dissipate that amount of power, for what time. Here you can see here that TD, the time duration is 50 microsecond. So for 50 microsecond we need to dissipate 300 watt of power. In this application we use SMBJ28A, which can dissipate 600 watt for 1 millisecond. So this can easily dissipate this amount of power in our application. Earlier with PMP 10652 design, we talked about powering ADAS processor and peripheral. Now let's move on to the remote camera module design, which communicates with ADAS processor through power line communication. This is a typical block diagram of an automotive camera module system. The optical data first, of course, is converted into digital data using a CMOS sensor, the image sensor. Here in this particular design, OmniVision digital image sensor OVT 10640 was used. Now this CMOS sensor will generate 12-bit parallel data. Now we need to serialize this 12-bit parallel data. TI's best-in-class TS90UB9138 serializer was used, which serializes the parallel data from image sensor and dump it on the power line. Also, there is an isolation between the power and the signal line using this high frequency filter, which is referred to as power over coax filter. Now with the wide VIN, DC to DC converter was used to provide power solution to the whole camera module, and we will go into detail of this new automotive DC to DC converter. PMP10653 is an automotive camera module rough-in design for uncompressed digital video system. This particular design is designed for start-stop condition, and we have done a lot of layout optimization for power as well as signal chain, which include the coax filter, serializer and mesh sensor. The front-end DC-DC converter used in this particular design is switches above AM band 2.1 megahertz. And the most important point of this particular design is to present a solution in as small size as possible. So this particular design was designed in 1 inch cross 1 inch space, board space. And all the parts that been used in this particular design is all automotive qualified too. Now we talked about the automotive front-end DC-DC converter LM53603 for ADAS processor, but we have also designed a different converter for a lower power application like this LM53600 as well as LM53601. So LM53600 is capable of delivering 650 milliamp and 601 is capable of delivering 1 amp of current. So this particular solution of course has a 2 megahertz performance, it's very small in size, but we have included SPET spectrum option here. So what is a SPET spectrum option? So in most system containing these switches, low frequency conducted emission from first few harmonic of a switching frequency can easily be filtered. Our most difficult criteria is the reduction of the higher harmonics which falls into the FM band. These harmonics often coupled to the environment through electric field around the switch node. Now LM53600 and 01 devices uses a plus minus 4% spread of frequency which spread the energy smoothly across the FM band but is small enough to limit the sub-harmonic oscillation below its switching frequency. So the peak emission in the FM band can effectively be reduced by more than 6 dB. You can see the results of conducted EMI performance of PMP10653 with SPET spectrum and without the SPET spectrum. So the design with SPET spectrum, you can see the smoothing of the peak, particularly at the higher frequency, and hence thereby comply with CISPA 25 class 5 regulation. And remember, again, there is no common mode choke as well as there is no shielding done here. Now here without this SPET spectrum, you can see all those peaks at the harmonics and may not comply with the stringent CISPA 25 class 5 requirements. So apart from EMI, power over coax filter optimization is most critical for any automotive camera module design. In power line communication, we have common power and signal conduction line. It's not like you have a separate power and a signal line. But if you view from the signal line, what you do is you introduce a high frequency inductor here, a high frequency filter here, which is nothing but an inductor. And if you view from the signal line, impedance of these inductor in the POC filter, the power over coax filter, which is this inductor here. So the impedance of these inductor in the power over coax filter increases as at higher frequency and won't allow any distortion of the data signal line. If you view from the power line here, so we use a DC blocking capacitor, and hence the DC line capacitor block the DC power influx into the driver, which is a serializer here. But the inductor of the POC filter allowed the DC current to pass through it. So you can assume the transmitter and the receiver here as being camera module and ADAS processor. Now, how to design this inductor which can isolate the signal and the power line? So an ideal 100 microhenry inductor could work as a low pass filter with impedance greater than 1 kilo ohm at frequency starting at 1 megahertz. However, due to parasitic capacitance, a real 100 microhenry inductor will cease to have high impedance around 70 megahertz. So you can see here the 100 microhenry inductor will have a self-resonance around here, and you'll see a decrease in the impedance. Now what's the solution here? The solution here is to add another parallel inductor in series, which is actually a 4.7 microhenry inductor. Now what it will do, it will ensure we have high impedance or wide frequency of interest. Now, but this size is, if you use this two inductor in series, the size will become unmanageable. So what is the solution? So the solution is we worked with our inductor vendor, and they came up with this particular inductor, which is ADL3225V -470 MT, which is a 47 microhenry inductor which has a self resonance beyond 700 kilohertz. Here, as you can see, 700 kilohertz here, which has been represented by the blue trace. So ADL3225V is represented by the blue trace here, and you can see here the self resonance occur at very high frequency, 700 megahertz, and hence it offers very high impedance over a wide frequency range, and you don't need to add any further. And this is again a very small inductor, and thereby you can achieve size optimization. So for more information, you can log on to ti.com/TI designs, and you can go on and search with the PMP number. With that, we have come to end of this presentation. Thanks for watching.